Hi, I'm Justin McGregor, the President and Project Lead for Titan Rover. Titan Rover is a two-part organization, an educational club and a URC design team with overlap between the two. The club's purpose is to inspire students to reach higher in space exploration and STEM education by using our past URC rovers and robotics demonstrations. The design team sets out to design and manufacture a complete rover for the URC. We now have 2 years of competition behind us and have learned some valuable lessons along the way. Last year, we developed Atlas from the ground up. This gave us a robust mechanical platform to work with, and we decided to make iterative changes this year and focus on the areas of opportunity we found through the analysis of our past performance. I am proud to introduce to you Calypso, based on the Atlas platform.
Beyond the lessons we learned from last year's competition, we decided to put the mechanical system through a series of rigorous tests to determine key locations for weight reduction to increase rover functionality. Testing provided valuable information, verifying that our system is robust enough to tackle any difficult terrain that is featured at competition.
Dual brush DC motors are mounted into each custom hub assembly in order to shield them from rocks. The tires have a custom tread design in order to increase our traversal abilities across sand, dirt, as well as steep slopes. We have prototyped and are currently testing a semi-active suspension system, which allows us to change the ride height and suspension settings at any time.
Using software provided by our sponsor Altium, we are designing a PCB that will shut off any subsystem that is drawing too much current. In addition, we have a physical kill switch with dual circuit control using an internal solenoid. This allows us to physically cut all power to the rover, as well as send a remote command to depower the mobility system in the event of an undesired movement.
The robotic arm is designed for both form and function. It features 5 degrees of freedom and utilizes carbon fiber limb that act as structural members while acting as an internal channel for all cabling and drive systems.
Feedback is designed into every joint of the robotic arm to enable real-time position of the arm and allow the use of inverse kinematics. The gripper can accommodate a vast array of objects using specialized gripper tips to maximize the points of contact on many standard and oddly shaped objects. The gripper can be field swapped for other types of end effectors if needed. The major joints and components of the arm have been designed with manufacturability and weight reduction in mind. Quick-release connectors for electrical and mechanical connections allow for easy serviceability during assembly and maintenance.
During the autonomous task, the rover is going to leverage the onboard processing cores in NVIDIA's Jetson TX2. We're utilizing both the GPU and the ARM processor on the computer vision system. We have built a custom model in TensorFlow for the tennis ball detection. Using machine learning, the model has accurately identified the tennis ball up to 16 feet away. Our navigation platform is based on a simultaneous localization and mapping model within the robotic operating system. Our sensors will construct an environment in which the rover will operate.
After reaching the provided GPS point, a mathematical algorithm will create a search pattern based off of known system and vision constraints. This will include any prior obstacles that the rover has encountered and added to the SLAM model.
Our sensor package uses a two-dimensional LiDAR unit, a centimeter-accurate GNSS, and an IMU. These components allow us to continuously update our position within our SLAM model. The LiDAR is mapping the terrain while the GNSS is localizing the position. By choosing Python in a module design pattern, we're able to seamlessly integrate these sensors to conduct unit testing and authenticate software verification and validation.
For this year's science system, we have refocused our efforts on collecting a suitable sample for our life detection assays. This involved designing a hollow stem auger that is able to collect and store a sample down to a depth of 10 inches while preserving relative superposition. In addition, our suite of sensors measures atmospheric variables such as barometric pressure, air temperature and humidity, UV radiation, wind speed, and CO2 abundance. Our in situ soil probe measures soil moisture and subsurface temperature. Our custom user interface logs and graphs the data from the sensors both on board and back at the base station, as well as records photos and video through our various camera systems. Our biochemical lab analysis consists of several tests to directly observe biologic organisms. Slide staining and UV spectroscopy will give us information on cell morphology, cell component structure, presence of genetic material, and endospore production. We will characterize the sample's chemical environment using pH testing and cation-anion identification.
Titan Rover continues to push the boundaries through rigorous testing and constant refinement. Thanks for watching, and I'll see you in Utah.